Hello class, this is Mr. DeVoe-Peterson and I'm going to go over chapter 4 for you, and we're going to learn about RF or radio frequency and how it relates to wireless networking. The big points are actually in this first paragraph if we go through here. So what radio frequency is, it's the high frequency, the AC current, if you will, that starts in a copper cable, right, from an infrastructure, a network, a wired network, and goes to the antenna of an access point or a modem router if it's at home. And the antenna then transfers a signal, the radio wave, over as a transmitter, and then the computer that's going to connect to it has a receiver, a wireless network antenna, and it picks up the signal. So this chapter talks about those characteristics, and there's a couple measurements that are real common when we talk about wireless networking. That has to do with watts, and more importantly for Wi-Fi, milliwatts, which is, a milliwatt is 1/1000th of a watt, and then decibels, right? A little less important might be the RSSI, the received signal strength indicator, that manufacturers sometimes take not so seriously when they advertise them on the box. So we see Wi-Fi in a number of different things. This map shows you computers, tablets, satellites, television, antenna, the works. But the most basic element, when we think of the wireless signal, the most basic element that we think about is the sine wave. And this is a picture of a sine wave. And it has a few characteristics that we're going to talk about after this image. But it starts here at 0 voltage. It goes up, and then it comes down, and it goes back to the 0 voltage. And this is one complete cycle of the sine wave, and they vary. And how many of these waves you'll see completed in a 1-inch space, and the strength of them, and so forth. So we'll learn about, in this next phase here, and we talk about the sine wave, the wavelength, the frequency, and the amplitude. And in some cases, because of Wi-Fi interference, the phase of the wave as it reaches the receiver. So here's a sine wave, and this is another really good example how one complete cycle at a time is a sine wave. So wavelength is how long does it, or what is the distance for that complete cycle of the sine wave to complete? And this here is showing you in inches, but it could very well be centimeters or inches. It depends on how high frequency of that wave you're dealing with. We know in wireless networking we deal with the 2.4 gigahertz, and then the higher frequency, the 5 gigahertz. And because the 5 gigahertz runs at a higher frequency, we're able to get more speed out of that Wi-Fi network. But because of the higher frequency, we don't quite get the distance of the 2.4. So coming back here, we'll look at frequency, another characteristics, and that's the number of cycles in a second. How many complete sine wave cycles complete in 1 second? Now the lower frequency, in this example, like the one I just gave you, 2.4, it talks about here, it has twice as far range as the 5 gigahertz, right? And it can penetrate things more easily because it is a lower frequency. There's less waves per second. The strength of that signal is the amplitude, and sometimes you can get a better strength out of that wave with a different antenna that acts as a radiator for that signal as it propagates through the air. And the phase is when the subsequent wave starts off and it's not in line. It's not in line with the previous wave. So this is an example where it's out of phase. In this case, I look at the starting points of each by 90 degrees, and that's part of the reason why Wi-Fi access points have multiple antennas to be able to accommodate that. Let's see, what else? If the waves arrive at the receiver at different times and points in time, you may get a corrupt signal, and that we know it happens also in wired networking. And what happens is you don't get the packet acknowledgement from the sender, doesn't get the acknowledgement that packet was received, so the packet is resent, and that happens in wireless networking. And it also happens in wireless networking, just like wired networking. This might be a test question, so I highlighted it. Hint, hint. The Federal Communications Commission is the regulatory agency in the United States, right? So I make a note of that here in the U.S. And it's different for different countries, but but the important thing is the local regulatory agency. There's not a global agency for that. The United States has the 2.4 and the 5 gigahertz bands. We know that radio frequency is divided into bands, and those further go in the channels. And I guess this first part is talking about 2.4. And notice, so we've learned that 2.4 can have up to 14 bands, but in the United States, we only get to use 11 of them. Notice that more in other countries, and in the 5 gigahertz band, there are bigger channels and there's more bands to use, and for that reason, a lot of companies like to use 5 gigahertz. And they can do is they can have access points that just do 5 gigahertz and accommodate more users. And since it's a company, they control the devices that users are going to use, and that ensures it stays on the 5 gigahertz. And we know since that frequency doesn't travel as far as 2.4, right, then there would have to be more access points placed around to accommodate users. Let's see, what else? I think there's some repetition here. So, but this is the big part for radio frequency range. So sometimes you just don't know, right, how many devices you need. Well, you know how many users you have to support. I'll give an example. I went to, I've gone to some of the Google I/O seminars at the Moscone Conference Center in San Francisco when they were having them there, when we were doing things indoors. And they gave us all access points and cell phones during one of those years. I can't remember which one it was, but there were so many people in the Moscone Center. I think 5,000 to 6,000 people. We just crashed the wireless network. We couldn't get online. The coverage wasn't set up for that. So how do you know how many access points to place? And that's kind of part of what you're going to learn in this class. But here's a big hint. What's coming down the road is you would do a wireless site survey where you would set up access points and decide where the better coverage is and how many users could be supported. That's based on not only how many people and how many devices, but what applications are they using? Are they doing voice over IP phones for every office and conference room? Are they doing high-end database or graphic video streaming applications? All those get taken into consideration for as far as capacity and then the coverage of the different areas. The area of coverage for wireless is called cell size. That might be a test question. And the book tells you early on here that having the widest coverage area and just doing one access point for one, I guess, kind of a larger space may not be the best solution, because those farther away from the access point get slower speed. So you need to think about where they are in relation to the access point and what their needs are as far as getting on the network. So there's a number of different things. Here's an example of what not to do for all these offices. You need to know what the usage are. This poor person in the corners, they're not getting any coverage, right? So obviously that's not the best solution. Though you don't want the coverage going too far beyond the building, right? So you would do some kind of site survey, and you may bring in software to do a predictive site survey, and the software takes into consideration materials and structure of the building and uses and all of that, which is quite a bit more expensive and more setup. Or you would do a physical site survey. We'll call that maybe an access point on a stick, and walk around and look at coverage. So it depends on factors like the size, the bandwidth of the applications, the obstacles in the room. Maybe there's a ton of filing cabinets in one wall. Say there's one right here, a bunch of filing cabinets along here, and here's the access point. These folks up here aren't getting coverage. So those are things you need to know, right? Transmission power, all that. So this next part here talks about some of those obstacles. I'll let you read it. And let's come down here. Also, it depends on the software you're using. I mentioned as an example, bandwidth intensive applications or voice over IP, the number of connected devices. One of the things here, we'll get into the channel selection here. Sometimes, I know when you configure your access point, you let it auto select. Well, you may not do that if it doesn't do a good job selecting the right channel. And an example of that might be, though you see one building here, but maybe you live in an apartment with a lot of apartments around you. You might do a little quick site survey and see what channels people are using. in your neighboring apartments and pick the one that's not being used. Say, no, I just want channel 6 or I want channel 1, depending on what people are using around you. So this is showing an example where all of the 6 access points here use channel 1. Probably not the best way to do it. It's better to do channel reuse and to ensure that there's no overlapping. Like 1 is next to 6, which is next to 11, and this down below here is 6, and we have 1, and there's very little overlap. So that is a good design. What happened to my mouse? I just lost my place. Let me go back here real quick, and here we go. Okay, another concept, and this has to do more so, I guess, for outdoors or perhaps down a long hallway connecting 2 wings of a hospital, if you will, and that would be the idea of a line of sight where the transmitters and receiver can see each other. Here's an example of a building, and then it introduces the concept to you of the Fresnel zone. I'm probably saying that wrong. Fresnel zone, and that has to do with, in this space here, what obstacles are nearby that line of sight, like trees that could grow and cause a problem later on, if you will. Redwoods grow really tall. They're not too big when you plant them, but a lot of trees in between here could cause a problem. So that is that zone. It's just a concept for you to know. And then we get into the concept of interference. And there's some examples here of items. As cell phones and microwave ovens are big items that can cause interference for 2.4 gigahertz. If you're near a lunchroom with microwave ovens, not good. Cold channel interference, that is, if you don't just do 1, 6, and 11, but you pick the channels in between here, there's overlap, and that's a problem. You want to do 1, 6, and 11 for 2.4 gigahertz. What else? Other items are Bluetooth, and I ran into that situation planning music for a celebration of life event with over 60 people and doing a wireless to a boombox. I decided that may not be the best way of doing it, so I turned off all the Bluetooth and wireless and what I was using to connect the music source to the boombox and just did a connected cable, and there were no problems with that. All right, so what are some things that can cause problems for that radio frequency, right? The transmitter sends it. What can happen? Well, it could run into a smooth surface, like a metal filing cabinet or a wall or tabletop, and that direction of the signal then bounces. So that can cause interference. Another thing that can happen if many of these glass buildings, like the new Apple building, a lot of glass and curved glass, well, that can cause a problem and can bend the signal. All right, so that's refraction. Diffraction, all right, and it sounds real similar to refraction, but diffraction is when it bounces around an obstacle, something like something in the wall or around a beam. The signal gets bounced around it. Scattering is when, now it's very similar to reflection, right, where it reflects off a surface, but in this case it's hitting a surface that's not smooth, it's uneven, and the radio frequency wave exits that impact in a scattered way. Absorption, and this might surprise you, absorption is when the radio frequency it gets run into something that converts it to heat, right? Now, what could do that? Well, in most cases, it's things like water or things like bricks and windows and drywall and things. The signal gets absorbed into it, it may not be able to penetrate it, and partially dissipate. One of the biggest things, surprise, surprise, are people, because we're mostly made up of water. So a busy office building with a lot of people packed, like a call center, if you will, packed together tight, there's going to be a lot of absorption of the signal, right? So definitely the signal, the access points will not want to be put it on the wall, they'll want to be put it on the ceiling so they don't run into as many people. Diffusion is just a characteristic where the wave dissipates the farther it goes. That's all it is. Now, this is the more technical part of it. Don't worry about knowing it 100%. It's touched upon again later in the chapter, but we know the basic unit of wireless radio frequency is the watt, and a measurement that's 1/1000th of a watt is a milliwatt, and most of what you'll see will be in milliwatts. It's a measure of the radio frequency power is what it is, right? And this could be a test question. What is the power leaving the access point? It is the absolute measure of power, right? Not what's received by the receiver, but the power leaving the access point is the absolute measure of power. So there's some calculations here. Don't worry about memorizing it. Watts a basic measurement, but milliwatts kind of what we deal with for Wi-Fi basically. And this is not as true as it used to be. So small office, home office access points have fixed output power. That's kind of changing. You can adjust the power on some of those small office, home office units. Maybe at one time they were that way, but what happens is the technology gets bigger, and the higher end enterprise equipment, it kind of finds itself integrated into the lower powerful SOHO type equipment, basically. Decibel relative to milliwatt. We're kind of getting into weeds here a little bit. This is technical. So decibel relative to milliwatt is a power level compared to a milliwatt. Don't worry about the algorithmic function. We're not here to learn that. But it again is the absolute unit of power or measurement. This talks about it here. You'll be using some of these measurements in software that you use to measure the signal strength as you walk around and do, like I've had to do in some installations where you do the Wi-Fi on a stick, where you could walk around with the Wi-Fi, or you can use an app on your phone and measure the strength of the received Wi-Fi signal for where you are. So this talks about it some more. The gain or increase in signal strength of an antenna, how strong that antenna is the, and those are characteristics of antennas. We'll learn about that a little bit later. What else? Here's a measurement. This number you'll be seeing. The receiver sensitivity of the dBm, and -75. In this case, what this chart is saying, that the minimum receive sensitivity of -17 dBm will make sure you can get 54 megabit of speed from a connected device. That's all it's saying. But you'll see this kind of measurement in the software you use to measure the signal strength. It'll be in a negative value, right? That's what it is. And this is showing you, okay, what is this? Oh, radio frequency noise. So what this is, and this is a concept you all know, being in a restaurant that's noisy, clinking glasses, silverware, and it's hard to hear everybody around the table, depending on how tightly packed it is, which we're not seeing a lot of that lately with the times we're in. But the point is, the noise around you, let's say you're at this table here, the noise around you affects how well you hear your neighbors at the table, right? Same thing for Wi-Fi. The other noise in the area from equipment, power sources, microwave ovens, and all the things that can cause noise generate another signal. So what this is here is a spectrum analyzer that shows you graphically some of the noise that's in that area where you're measuring your output, and there needs to be enough separation from that flow noise and the signal you're receiving to get a good transmission. So the lower than, let's see, how do I say this? This is a negative, so it's a little confusing. So this signal is not as strong as -75 dBm. It's because it's a negative number. So the concept is a little confusing until you use the software and do a site survey. So just know that these are just measurements of looking at all the interference noise around that zone where you're trying to receive a signal compared to the signal strength you're able to receive. RSSI signal receive signal strength indicator is I wanted you to see that. It is arbitrary by the manufacturers. That's somewhat irritating. But they can't guarantee that signal strength because they don't know what environment you're putting that equipment into. So they can't make a lot of guarantees because they don't want to get sued. So you'll see, there's groups and reportings of success and failures of different manufacturers of access points and how they work in different environments. And those are your sources to make sure that you will have success in that employment of the access of the wireless deployment wherever you put it, in whatever building it is, right? So this is saying here, I didn't highlight it, but they're saying that the negative dBm, okay, in this case, minus 10 dBm is not enough for an adequate, not adequate. They're saying you need 25 dBm separation from, this is the floor noise, and this is the signal received. You need that kind of separation in that measurement. And once you know that with the software and hardware you're using, you're not worried about how to calculate those numbers. You're looking to see. In this case, VoIP want negative 67. That's a higher signal strength than negative 75 dBm, surprisingly enough. So that is chapter 4. A little technical stuff at the end, but just kind of stay focused on what we're looking at for the different types of radio frequency signals, and the things that can cause interference or cause a signal to be stronger and cover a bigger range, and things like the users and the applications they're running to help you determine whether that'll meet the needs not only today but in the future, as people bring in their own tablets and cell phones and other needs, and traveling salespeople come back to the office. You really have to overplan the capacity of the wireless network to ensure success. So that's it for now. Read chapter 4 and send me emails if you have questions. Okay, good luck.